Dr. Rao, can you see my screen?
Yeah, I can see it. Yeah.
Okay. Let's start the lecture. Okay. Good afternoon, everyone. I'm Li Qiangli from Tianjin University. Welcome to our series virtual academic seminars to celebrate the launch of SmartMed. SmartMed is an open access journal co-launched by William and Tianjin University. I'm one of young editor members of SmartMed. The editor-in-chief of SmartMed are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from City University of Hong Kong. Today, Dr. Akshay Rao from Cavendish Lab, University of Cambridge, will give us the presentation. Now, I would like to make a brief introduction to the speaker. Dr. Akshay Rao received his undergraduate degree from St. Stephen College, University of Delhi in 2006, and his master's degree from University of Sheffield in 2007. He received his PhD degree from the University of Cambridge in 2011, working in the group of Professor Sir Richard and Friend, following which he had a junior research fellowship at Cambridge. In October 2014, he started his independent research group in the Cambridge, supported by an EPSRC Early Career Fellowship and a Wilton Advanced Research Fellowship. Akshay currently holds the Harding Assistant Professorship at the Cavendish Laboratory in Cambridge. His research group, which consists of about 20 PhD and postdoctors, is interested in the optical and electronic properties of next generation energy materials. The group studied these materials with novel optical spectroscopies and macroscopies, as well as using the insight gained to develop new materials and devices concept. Akshay is also a co-founder of two startups, Cambridge Photon Technology and Cambridge Vision. Today, Dr. Akshay will give us the talk about the Exatron Transport in molecular semiconductors. Let's welcome Dr. Akshay. I will stop my sharing, then you can start your lecture. Yeah, you can meet it.
Thank you very much for the introduction.
Okay. Now you can share your screen and start your lecture. Thanks.
Perfect. Can you see my screen?
Yeah, I can see it.
All right. So thank you very much for the introduction, and thank you very much for inviting me. I'm very happy to give this lecture. So today I'll be talking about Extern transport in molecular semiconductors, organic semiconductors, and we'll try and keep this lecture pedagogical in style so that hopefully the master's and PhD students can learn something from this. And I'll share with you some of our latest research in this area. So to begin with, let me introduce my group. We are based in the physics department, the Cavendish Laboratory at the University of Cambridge. Cambridge, of course, a very old university, very long tradition. The Cavendish is where the electron was discovered about 100 years ago now by J.J. Thomson. So very rich history. My group is doing much less important work in the grand context. But we're a group of about 20 people, a mixture of physicists and chemists. And we're interested in the area of energy materials. So what do we mean by this? So as you all know, the world is undergoing a transformation in the way we generate, store, and use energy as we shift to a more sustainable and renewable energy-based economy. And as scientists, this provides us a very unique opportunity to help bring about this transformation to a more sustainable and renewable way of generating and using energy. And this requires the development of new materials and new devices. So our existing technologies are kind of not good enough to kind of get to net zero by 2050. We do need the development of new materials, new devices with advanced functionalities beyond what is possible today. So this is true across a range of areas. So in semiconductors, we are interested in materials for solar energy harvesting, for lighting, high power electronics, and say optical switching, things like this, low power computing. Of course, there's a great interest everywhere in battery materials of various kinds for long-term, short-term storage, grid scale, electric vehicles, etc. And of course, there are other technologies like thermoelectrics, which could help in this transformation a lot. So broadly speaking, my group is interested in the electronic and optical properties of these materials. And we have 4 research themes within my group. The first is understanding the electronic and structural dynamics of these materials. So that is to understand not just the nature of the electronic wave function in these materials, how electrons or excitons, the dynamics, but also the combined structural dynamics. Another aspect of this work is to study the transport of energy and quasi-particles in this material. A more recent area for us is studying ion transport in battery materials and mixed electronic ionic conductors. And lastly, we hope to kind of use the insights we generate from our spectroscopic and microscopic studies to develop some new materials concepts, some new device concepts. But for today's lecture, we'll focus on just one area, and we'll focus on this aspect of our work, which we call quantum transport in semiconductors. And as I'll show you, this is kind of very rich area, and we are kind of learning lots of very interesting things. So let me just give you a brief overview of what we'll talk about today. To begin with, so that we are all kind of understand what we're talking about, how we're on the same page, I'll give a basic introduction to excitons and extern transport in molecular semiconductors. To a lot of you, this will be very familiar, so you just have to bear with me while we just discuss some basics, perhaps for some people who are not so familiar with this. We'll talk briefly about FRET, that is Foster Resonant Energy Transfer, which is kind of considered the dominant mechanism for exciton transport in organic materials. We'll then briefly talk about coherent exciton transport, what it is, and whether it's a feasible sort of means to achieve exciton transport in devices. We'll then kind of discuss a little bit about how best to actually study and measure exciton transport. And after that, I will come to the main part of this talk, which is 2 stories, which we have kind of established over the last few years. One is transient exciton delocalization, and the other is about cavity-free polaritons. Right? So we'll start with the basics, what we understand of the field, what the kind of current paradigm is, and then I'll end with hopefully what I believe are 2 new paradigms for exciton transport that could completely change the way we look at organic semiconductors, organic semiconductor-based devices, and then hopefully the renewable energy devices which are based on them in the future. Right. So for the students or the postdocs here, I thought I would start off with some references so that you can look back on the recording of this lecture. These are kind of three references which I'll use extensively during this talk. The first is a very, very nice book on organic semiconductors. Perhaps all of you are already familiar with it, by Anna Kola and Hein Basler. If you have not seen this, I highly recommend it. It's a great book. If you can kind of learn everything about organic semiconductors, if you have the patience to study it. The next is a very nice paper from Quen and Paul Blom and Olex, and this talks about exciton diffusion. It's a very beautiful review paper. Again, I highly recommend it. And the last is a review paper by Professor Brixner in Germany on natural photosynthetic antennas and artificial systems based around them, more on the exciton transport in molecular aggregate systems. Okay, so these are very, very nice papers, which can give you a lot of information. And I'll use them extensively during this talk. Right, so let's go back to the basics. And you'll all be familiar with this, but excitons are bound electron hole pairs which form in molecular semiconductors. For today's talk, we won't talk about other kinds of excitons in other materials, 2D systems, etc. We'll focus just on the organic excitons. And so excitons are formed either by light absorption, which promotes electrons from the HOMO to the LUMO of the material. And then you get a Coulomb interaction between that electron hole, which binds them together in a quasi-particle known as the exciton. Now, of course, what happens is the energy of these exciton states is almost equivalent to that HOMO-LUMO gap, but it isn't quite that. It's not the HOMO-LUMO gap is the transport gap of the molecule. The exciton energy is slightly lower. So of course, the Coulomb interaction pulls new levels into the semiconductor bands, and you get an exciton state which is slightly lower than that transport gap. And as you can see in this very nice diagram, again taken from this very nice paper from Paul Blom, review paper, Once you get the formation of excitons, which are normally sort of denoted with this S1, S2 terminology for singlet excitons, there are a number of processes that can happen. You can have radiative recombination, as illustrated by this process 2, which gives you light back out. And of course, this is of interest to us in LED or lighting applications. You can get non-radiative recombination, as illustrated by process 3, or you can get intersystem crossing to spin 1 triplet exciton states. And so what we are really interested for the purpose of this talk is exciton transport. So how we move excitons from one site to another. And what this diagram I'd like you to kind of keep in mind is that excitons have a finite lifetime. So once we form the exciton, we have some finite lifetime before that exciton will recombine, either radiatively or non-radiatively. And within that finite lifetime, we have the problem of moving this exciton to wherever we need to move it to in order to do something useful. That might be light emission, that might be charge separation at a heterojunction, etc. So we have this finite lifetime in which we need to move excitons. Now, exciton transport is a really fundamental problem. And it's a very interesting sort of problem to deal with. And in many ways, I always say that it helps to power the biosystems of the Earth. So as you know, in photosynthetic organisms, so this is green plants or photosynthetic bacteria, the photosynthetic apparatus consists of a reaction center where the exciton is broken up into electrons and holes, and those electrons and holes are then used to drive redox chemistry, which then powers life. But before that step, you have these sort of antenna complexes, which are organic chromophores, which absorb light, create excitons, and then they funnel those excitons to this reaction center. And in fact, this happens over a time scale of sort of femtoseconds to tens of picoseconds, and over distances which are tens of nanometers. So the idea here is that without these light harvesting complexes, life on Earth would, as we know it, would not be possible. So these excitons are the kind of key unit of energy that is powering photosynthesis, right? So the excitons have to be moved from these light harvesting antenna to these reaction centers. And over billions of years of evolution, nature has evolved this very, very beautiful kind of complex protein structure, which holds together this scaffold with really angstrom level precision. So it's a kind of self-assembly that we as humans are not yet capable of achieving, but it's a very, very efficient process. So excitons in natural light harvesting systems are funneled tens of nanometers with 100% efficiency to the reaction center. And it sort of goes downhill exactly to the right point every time under all conditions, right? Even though this system is, of course, consisting of organic molecules, where normally one would associate to have some dynamic disorder, perhaps static disorder, all these things, nature has kind of overcome all these problems and generate this very, very efficient exciton funneling system. Now, if you kind of turn to our normal organic semiconductor devices, and we ask and we sort of try to seek inspiration from nature, the question is, what do we want to achieve? What is our target in terms of exciton diffusion, right? So in an organic semiconductor system, very commonly, in a very, very simple sort of picture, for instance, for an organic photovoltaic device, you would want to have a donor acceptor in a bilayer architecture. This is the simplest thing we could do. And it would also be the best kind of system from the point of view of long-term stability, from the charge extraction point of view, and from the VOC point of view. This would be the kind of ideal system. And this is, of course, for those who are familiar with this field, the first organic photovoltaic devices made by Tang and colleagues, Professor Tang now back in Hong Kong, were based around this concept, just a very simple bilayer system. But the problem, of course, as you will all also know, is that the exciton diffusion length in our organic semiconductor materials is normally very short. So what is the target that we would like to have? So ideally, you would want to have your exciton diffusion length be equivalent to the full optical absorption depth of the material. That is to say, if you have light incident on a film of your organic semiconductor, then in about 100 to 200 nanometers thickness of the film, you'll be able to absorb something like 99% of those photons. And then ideally, the exciton diffusion length would be equivalent to that depth that you're required for the complete absorption of light. So roughly speaking, what we want is an exciton diffusion length on the order of about 200 nanometers to be safe. So if that happened, if you had a material which had an exciton diffusion length of about 200 nanometers, you could build a simple bilayer heterojunction system, and you could ensure that all the excitons generated in these materials reach that donor acceptor junction. Now, of course, this is not the case. Most organic semiconductors that we've been dealing with for the last 20 years or so have exciton diffusion lengths actually more like 10 nanometers. And that's why we use a bulk heterojunction system, which many of you will be familiar with, where we blend together either by evaporation or solution casting, spin coating, etc., a organic donor and acceptor material, and we try to form this complicated nanoscale morphology where the domain size is on the order of 10 nanometers, which is the exciton diffusion length of the system. And as you know that empirically, we've had a lot of success with this. Organic photovoltaics have now reached about 19% single junction efficiency, which is sort of it's really incredible actually, if you think about it. But the formation of this bulk heterojunction is very complicated. Its long-term phase stability is also a complex problem. These kind of materials, of course, from a thermodynamic point of view, want to phase segregate over time. So maintaining this structure is challenging. It also compromises to some extent the charge extraction from the device, which then leads to sort of problems with the fill factor. And ultimately also it lowers the VOC just because of the fundamental thermodynamics. So although we've made this tremendous progress with bulk heterojunctions, really in an ideal case, we would have a bilayer heterojunction if we could. And if you think about other applications for organics in terms of light harvesters, whether that's for photodiodes, it's the same problem. If you want to do photocatalysis, which is now an increasing area, so photocatalysis using organic semiconductors, it's exactly the same problem as well. You really want to have, a simple system, kind of bilayer type system, or even a simpler system where you transport energy through an organic semiconductor to a redox active site at the end of that, without having a complicated donor acceptor type morphology, right? So our target is to try and achieve these diffusion lengths of about 200 nanometers in these systems. Now, classically, we tend to think about excitons as localized particles, right? So we think of them as point-like particles which hop from one site to another, okay? And they sort of move in an energetic landscape where there's disorder. So this can be dynamic disorder, static disorder within a landscape. And the exciton will move from site to site within this and perform a random walk. And this is how the exciton moves, right? So there's no particular preferred direction for the travel. It's just hopping from site to site to site in a random walk, and it will go towards the lowest energy site as a function of time. So that's the picture of incoherent sort of particle-like transport of excitons. There is another picture about this. We can also think about the excitons as waves. So, from a quantum mechanics point of view, an exciton is a quasi-particle which should behave like a wave, and it has a wave function, and it will have a band structure. And so one can say, well, exciton should move coherently. That is to say, with a fixed phase relationship in a wave-like manner through our molecular semiconductor. So there are these two pictures. The hopping type transport is the dominant picture that we use to actually model the organic semiconductor materials that we work with, and we'll talk about that a little bit. But just keep in mind that there is this coherent transport model, and we'll come back to it in a second. So let's start with the kind of incoherent picture. So this is the idea that, of course, our exciton is localized on a single organic chromophore, and then it will move from site to site. So this interaction can happen via two methods. So the first is actually Dexter energy transfer. And the idea here is this is a correlated double electron transfer process. So we get one electron transfer from one molecule from the donor to the acceptor, and a correlated electron transfer event backwards. So Dexter energy transfer can happen for singlets or triplet excitons, but it is a very slow process. It's basically, it's two charge transfer integrals together. So it's much like it's mediated by the same nearest neighbor site-to-site interactions, just as charge transport is. And it is by its very nature, because of this, a very slow process, okay? And requires close orbital overlap between the neighboring sites. So although it can happen for singlets or triplet excitons, when we're normally talking about singlet excitons, which are formed by light absorption, we tend to not deal too much with Dexter energy transfer. Of course, for triplet excitons, there's no dipole moment, which are dark states. Dexter energy transfer is the dominant mechanism of transport. But for singlet excitons, normally, we deal with the so-called FRET or Foster Resonant Energy Transfer mechanism. And the idea here is that our molecules, you can think about them as little antennas. So our donor is a little antenna and our acceptor is a little antenna, and that we can, through space, transfer energy from one antenna to another, right? So this is, you can think of it as, it's just electrostatics. It's the Coulomb interaction between these antennas. And so what happens is we have an exciton on a donor side, that exciton drops down, and you get a virtual, that is to say, photon-less transfer of the energy from our donor to the acceptor side, which is then excited. And so by this means, energy can sort of transport between molecules, but now through space, you don't require an orbital overlap. So in principle, the FRET mechanism can act over any length scale, but of course, there's a sort of a realistic length scale of which you can act on. But again, this happens sort of in a point-like manner. So the exciton jumps from one molecule to another molecule, then the next molecule, so on and so forth. And of course, it will not jump uphill in energy. So it will always go downhill in energy. And so you'll move in an energetic landscape downhill. Now, the physics of exciton transport via FRET have been worked out for a very long time. It's all very well understood. And you can work it out quite simply. It's a sort of, let's say, master's level or even undergrad level problem in electrostatics, really. And if you're patient enough, you can sort of do the derivation. And you can work out that the rate of energy transfer of the exciton from one molecule to the next is proportional to sort of the distance between them to the inverse 6th power, right? So as I move my donor and acceptor molecules further apart, there's this to the power 6 dependence on the distance between them. And so the rate of transfer falls off very, very quickly. And you have this sort of very long, complicated R0 term here, which is given by this. But essentially, the thing to keep in mind is that FRET is normally within this point dipole approximation, right? So we treat our molecules like point dipoles. And this works very well for molecules in solution, for instance. If you have a molecule in solution, they're clearly acting like point dipoles. Or if you have a film of organic semiconductors, but the film is very disordered, then again, the FRET approximation works really well. And in fact, if you were to look back in the literature of organic semiconductors for the last 20, 30 years, we have mostly talked about the FRET mechanism and dealt with transport within this FRET mechanism. So this is by far the dominant model for our understanding of organic semiconductors, for exciton transport in organic semiconductors. And what happens, of course, in this model is that we then move in time. As I said, we move from one side to another, always downhill in energy, but in a random walk. And you can then work out a diffusion constant, again, from this rather simple physics of the system. And you can also work out the diffusion length for your excitons. And you can put in various parameters, and various things have been measured over the years. But essentially, the long story short is that it is very, very hard to achieve diffusion constants, which are greater than 0.1 using FRET, or diffusion lengths above 40 nanometers. In fact, for most of the organic semiconductors that we deal with, especially, say, polymeric films or disordered small molecule films, we're normally talking about exciton diffusion lengths on the order of 10 nanometers. Okay, and this is why, of course, we've had to develop and put all this effort into developing bulk heterojunction systems, because we can't get the excitons to go very far, and we're limited by this FRET-like transport of excitons. So this is the kind of essential framework that our field has worked with for the last 3 decades. Right. So let's take one step back, and now let's consider actually if one were to think about this from first principles. One would say that, when one creates an exciton, there is an exciton band structure in our material, because the exciton is a quasi-particle, so wave. And in fact, from first principles in quantum mechanics, you would say that the exciton should actually move at a group dispersion velocity, which will be the derivative of this exciton band structure. Okay, so just like I have a band structure for my electrons in my material, I can also calculate a band structure for my excitons in the material. And then we would expect that the exciton would move at basically, the derivative of any point in K space that would give us the group dispersion velocity. And if you look at that picture, you would say that actually the diffusion constant should be much greater than 1, that's centimeter square per second, and it should be actually relatively simple to achieve diffusion lengths greater than 200 nanometers. And I said 200 nanometers at the start of this lecture. That was our target. We want to have exciton diffusion lengths about this length scale so that we can get complete light absorption and complete transfer of the excitons to an active site for charge dissociation, for photovoltaics, or photocatalysis or something like that. But of course, this is not what's happening in most systems. And the reason is very simple to understand, in that, unlike a very highly crystalline semiconductor system at low temperatures, so say gallium arsenide at 5 Kelvin or something like that, in organic semiconductors at room temperature, there's a lot of disorder and there's a lot of scattering. So what happens is, although when you initially generate that exciton state, it is a wave function which could in principle move coherently, you get very fast scattering, right? So you scatter with phonons, with other excitons, with defects. As when I say phonons, of course, I mean molecular vibrations really in the organic systems, with charges. And all this happens on very fast time scales. And then we will localize that exciton state. So initially, we should have some period of time where the exciton could move. Sorry, is there a question? Should I continue? Okay. So essentially, this scattering of excitons happens on very fast timescales. And in fact, it means that in most of the organic systems we deal with, there is very little or no coherent motion of excitons at all. Okay. Some of you will know, those of you who kind of have followed the field of photobiology, that there has been a debate in that community for a very long time now, almost 20 years, of whether coherent exatron transport plays a role in natural light harvesting systems, which, as I showed you before, have a kind of level of order where, which sort of through evolution, they've achieved a level of order which our normal organic semiconductor materials don't have. So that's still an open and very interesting question. But in most of our standard organic semiconductors that we use in devices, this coherent exciton transport process plays basically no role. So we seem to have a problem in the field. We have two regimes of transport. So on one side, we have FRET, where we have localized excitons, which move from site to site. And the other, we have coherent transport, where we have delocalized excitons moving in a wave-like fashion. So the ideal kind of mechanism for us is actually coherent transport, because it's very fast and we could move excitons very far within their finite lifetime. But in fact, what happens is that you get scattering in real materials and everything localizes very quickly. So in the tens of femtosecond time scale, everything is localized, and then we don't get any sort of coherent motion. But on the other hand, with FRET, this is the mechanism that applies to most of our materials, which have high dynamic disorder, such as strong electron-phonon coupling. They have high structural and energetic disorder. And especially this is given when we are solution processing them, okay? And we have sort of, let's say, only very partial order in these systems. So that's our kind of normal picture for organic semiconductors. The coherent transport, there are examples of it in very highly ordered J aggregates, for instance, especially at low temperatures. There's been some beautiful work over the years. And there's this ongoing controversy in natural light harvesting complexes, whether this is the kind of dominant process. But from a device point of view, coherent transport doesn't play a role. It's FRET that seems to dominate. So the question is, can we do anything in the middle, right? We can't have systems where we have very beautiful order and very low dynamic disorder. That's just not the nature of organic systems. What we're dealing with is normally room temperature and a finite amount of disorder. And so nowadays, our material systems, especially in the transistors, the non-fullerene acceptor systems, etc., are actually kind of operating in this regime here, where the systems are not highly disordered from an energetic point of view. There is still disorder, but there's much less disorder in the materials than say materials we were working with 10, 15 years ago. And so the question is, what is happening in this intermediate regime, where we don't have a lot of disorder, but we don't have a high amount of order as well? We're in an intermediate regime where we have partial order, perhaps partial crystallinity. So can we do something sort of different in these classes of materials? Now, I'll just take 1 second to talk about how to measure exciton transport. This is a table I've taken out of this, again, this very nice review from Paul Blom. And this sort of gives some of the standard ways to measure exciton transport. And traditionally, this is mainly done with sort of quenching or annihilation-based measurements. So that is, you look at the lifetime of the exciton, and then you put a quenching layer in the film, and you look at the change in lifetime, or you create lots of excitons that annihilate with each other, and you look at the kind of quenching dynamics, and you look at the change in photoluminescence lifetimes. So there are all these kind of methods that have been used. The problem with all these methods that have been used to date is that they give you only a time averaged and spatially averaged picture of exciton transport, right? So what you do is that you look at the exciton transport across the entire lifetime of the exciton and over the entire sort of spatial region of your sample. But if you were to look at an organic semiconductor, say in a TEM, so this is some data from our group, where we're looking at some P3HT nanofiber films in TEM, one of the defining features of organics is that the films are not homogeneous, right? We have disordered films on a variety of length scales, from nanoscale to micron scale disorder. And if you look at various points over here, so these sort of labeled points, this is scanning electron diffraction at various points, you can see that we can detect crystallinity in some of these systems, but it's very different at each point, right? So our films have some crystallinity. They're not completely amorphous, but they're not completely ordered as well. And if you look at each point, each of those points looks somewhat different, right? So crystallinity is varying, the domain sizes are varying. This is not a single grain, single crystal material. And of course, on top of this, there's dynamic disorder as well. And so the real problem with all the methods that have been used to study exciton transport till now is that they give us no idea of the spatial inhomogeneity of our materials. So how different parts of the film actually behave differently. So the kind of structure function relationship is absent. We don't know anything about that. And the second thing is that they give us only a time average picture. So we don't know actually what is happening at early times versus what is happening at late times. But we know that excitons show non-equilibrium dynamics. So the dynamics on sub 100 femtosecond timescales are very different from, say, at 100 nanosecond timescales. So really what we need is methods which can bridge this gap, right? So what we need to study exciton transport is a method that can watch excitons, image them on femtosecond timescales and with nanometer spatial resolution or spatial precision, okay? So that then we could actually look inside our organic semiconductor films and follow the excitons from the moment you create them to the moment they decay, and watch their entire trajectory and figure out what's going on, right? So that's our challenge. Do we have a microscopy? Can we develop a microscopy method that can do this? Now, a number of years ago, well, about 20 years ago, the structural biology community made a revolutionary sort of breakthrough in optical microscopy. And this was the birth of sort of single molecule and super resolution imaging techniques. So you might have heard of some of these techniques like STED or PALM or STORM. And what happened with these techniques is that when you looked at fluorescence images in biology of, say, cells, you got something that looked like this, right? So this is sort of a micron scale scale bar. You got some blurry image like this. But using these super resolution techniques, you could then localize the photoluminescence down to very precise points. And this image converts to this much clearer image over here. And the way this is done is via single molecule localization. That is, you look at fluorescence maps, average over time, and then you localize the exact sort of pick the tops of the sort of fluorescence Gaussians, and you localize these points in time. So this is a kind of revolutionary discovery, which led to the Nobel Prize in Chemistry being given out in 2014. And because of the kind of, the dramatic effect it had in biology and structural biology for the study of living systems, right? So nowadays, if you go into a structural biology or biochemistry laboratory, every good laboratory will have a super resolution microscope, right? So this is a kind of revolutionary technique, and it enables this resolution, optical resolution, down to 2 nanometers nowadays in the best cases. It's really fantastic technique. So in some ways, that's the kind of course, resolution that we would like to have in organic semiconductors. But the problem is that this method is based on fluorescence. So you need something to emit. And we want to watch excitons before they decay. So we don't want to watch excitons emitting. We want to watch excitons during their actual life cycle, not at the end of the life cycle. And the other thing, of course, is that this technique has no time resolution, right? So this is a time averaged PL methodology. What we are interested in is actually a time resolved technique. So we set out to kind of tackle this challenge about 5 to 6 years ago when I started my own group. And we did what we thought was the simplest thing which we could do, which is that we already did pump probe spectroscopy. For those of you who are not familiar with this, the idea in pump probe spectroscopy is that you generate a very fast pump pulse in time, down to 10 femtoseconds, and you create photoexcitations in a sample. And then you come in at some time delay after that with a probe pulse, also very fast in time, and you can probe the changes in your material. So this allows you to study the excited state dynamics in materials with down to 10 femtosecond time resolution in the kind of visible and near infrared time regime. So this is a well-established technique. What we did was to couple this with a wide field microscope. So the idea now is that we take our pump pulse and our probe pulse, and we now, instead of doing spectroscopy, we image our sample in time, right? So I'll skip the technical details. There's all sorts of tricks in terms of optics here. But the key thing that I'd like you to focus on is the following. So let's say we have our nanoscale object. Let's say this is a polymer over here represented by this black squiggly line. What we do is we generate an ultra-fast pump pulse, which will come in. So this pump pulse is about 7 femtoseconds in time. And this is represented by the green area here. So we excite our material and we create excitons in that material. And then we come in at various time delays after that, say at 2 femtoseconds, 5 femtoseconds, 10 femtoseconds, etc., out to nanosecond time scale, with a probe pulse represented by this sort of pink area here. But the probe pulse is now wide field. So what we're doing, and that will then go on to a CCD camera, and we image this entire area, right? And so what we see at very early times, you'll basically image this profile of excitons that you have created in your material, right? So, and that might look something like this. So this is the profile in dark blue here, in the top blue color here, that you might image. And then we come in at a later point of time. So let's say we imaged at 20 femtoseconds, then we image at 30 femtoseconds again. And what's happening is those excitons will move, right? So we have created excitons as material, they start moving and the spatial profile changes. And we come in and we take a snapshot at that. And we do this for 40 femtoseconds, 50, et cetera, et cetera. Now, all this is limited by diffraction. So this image that we measure, the 20 femtosecond image, is limited by diffraction to whatever wavelength is lambda by 2, where lambda is the wavelength we're imaging at. And the next one is also similarly measured by diffraction. But if I subtract one image from the other image, then I'm no longer limited by diffraction, because now I'm just subtracting 2 images. And you can do that to any sort of spatial precision as long as your signal to noise is good enough. So this is exactly like the trick that is used to localize the peak of the photoluminescence in the super resolution microscopy techniques. But now what we're doing is we're subtracting 2 absorption profiles, right? So what we're looking at is not PL, we're looking at the photo-induced absorption of the excitons in the material. And so we can do this at any time. We don't have to wait for them to decay. What that allows us to do is basically with sub 10 femtosecond, about 7 femtosecond time resolution, we can look at the motion of excitons with this spatial precision below 10 nanometers. And in the best case, we can do this now with a spatial precision of about 2 nanometers, right? So we can essentially watch the flow of excitons or charges or polaritons or any other kind of particle that we can create with light. We can watch the flow of this really down to the nanoscale with very high spatial temporal precision. Okay, so that's the technique we'll be using for the rest of this talk. And essentially, this is kind of what the data looks like. One measures these Gaussian profiles, and one can see essentially that we can see expansions. So this is to say the motion of excitons or whatever quasi-particle we have. We can measure this with about 10 nanometer precision very routinely in the best materials. If we try very hard, down to 2 nanometers, and the time resolution is very high. Something that we won't talk about today is that we can also do time resolved Raman using this, because we have very fast pulses, but we can get chemical information as well, so chemical mapping. So this has been a kind of effort in my group over a number of years. Some very, very good PhD students and postdocs have kind of taken this project on. And we worked very closely with Professor Philip Kakura from Oxford, who's pioneered this work with us. So that's our methodology. I'll be happy to answer any questions about that later on. So I'm just going to open the window here. So having established that, let's talk about the first story actually that we have today. So we're done with the introduction. And so the first story is basically about a new way to harness exciton-phonon coupling in organic semiconductors, which leads to this transient delocalization mechanism that we have proposed for Exatron Transport. So you can read more details in this paper here, which was published in Science Advances last year, and I'll go through some of the key details now. So essentially, what we're looking at here, we have a model system, which is based on P3HT. So for those of you who have been in organics, especially the senior professors, P3HT is a material system that we've never been able to get rid of. We've been working on it in some form or the other now for almost 30 years. And of course, a lot of work went into it in the 2000s on P3HT PCBM solar cells, for instance. Thousands of papers have been published. And it is quite a nice material in many ways. So here we have a slightly new twist on P3HT. And these materials are made by Professor Ian Manner's group in the University of British Columbia in Vancouver. And essentially what you have is you have a P3HT chain, which is kind of capped off by this group over here. And what this allows us to do is that we can sort of crystallize these materials and grow fibers up from them through this methodology, which is called Crystallization-Driven Self-Assembly. So it's a living kind of self-assembly method. And what happens in this is that essentially you get stacks of P3HT, and then these things stack one after each other. So you get about three P3HT chains, which go one on top of each other. And then these three sort of form with another three and another three and another three and so on and so forth. And you grow these nanofibers controllably. So you can have a length of these nanofibers from 50 nanometers out to a few microns, if you like. And this can be very well controlled. So essentially you get this very nice stacking of P3HT nanofibers in this direction. So coming back to this picture I already showed you. So this is now a high resolution electron microscopy image of these films. You can see these nanofibers. And then this is a orientation map of those fibers. So what you can see here is how long those fibers are before there's any twist in them. So these are very, very long objects. And on average, it's about 80 nanometers before there's any wiggles or twists in them. So they kind of have 80 nanometer regions, which are nicely crystalline. So this is a kind of cartoon image of what we can imagine these things as. So we have chains of P3HT, which are stacked very nicely with each other, forming this nanofiber. Whereas if you took P3HT and made a normal spin-coated film, you'd have regions which were crystalline, regions which were amorphous, and then mixed regions between them. So this is a kind of normal sort of spaghetti picture that we get with P3HT, whereas this is this sort of nice crystalline picture that we have with these materials. And this enables something very extraordinary to have this order. So what we're going to do is this pump probe microscopy technique I just walked you through. So we have this very high time resolution, very high spatial precision, so we can watch very precisely the excitons in time. So this is our absorption spectra. You can see that there are two absorption spectra here, that of normal P3HT and that of our nanofibers, the blue and the red. And you can see there's almost no difference. So the materials behave like normal P3HT in terms of their optical absorption because they are just chains of P3HT, but they're now stacked, but they have no extra coupling between them. So they're just still P3HT. And what we then do is with our optical microscopy, we can measure the diffusion constant. So we measure the motion of these excitons. We're looking at their transport in time out to several tens of picosecond time scale. And we can fit this very nicely and get a diffusion coefficient. And we get a diffusion coefficient of 1 centimeter square per second. Right? This is 100 times larger than you would expect for normal P3HT. Okay, let me say that again. So we get a diffusion coefficient of 1. And that's 100 times larger than one would get for P3HT. And you can see we can do this here. So this is our nanofibers. You can do some statistics on this. If you take normal P3HT, essentially you measure something that is basically within the signal to noise of our system. It basically isn't moving. If we take our nanofibers, we do a control experiment where we break the crystallinity, break the order in them by just putting some chloroform on them, which breaks the nanofiber apart. Again, we get a number of basically 0, right? So, but within our well-ordered nanofiber film, so this is, remember, this is a film now, which is absorbing visible light across the visible spectrum. Those excitons are being transported 300 nanometers on average with a diffusion coefficient of 1, right? So here is a system in which we have achieved this target. So I mentioned this target of about 200 nanometer diffusion length for exciton transport. Here we've achieved 300 nanometers, which is on the order of 15 to 30 times more than normal P3HT. So if you took regular P3HT, spin-coated a film, you would expect exciton diffusion length somewhere around 10 to 15 nanometers. So this is, this is very, very much higher than that. So the question is, what's the mechanism of this? What's actually going on? And so I'll skip a lot of details, but with the help of some theoretical colleagues, a group of David Beljean and Mons in Belgium, we looked at these materials and we simulated various sort of cases for them. And the key thing that comes out is the following, that if you consider these materials to operate within the FRET regime, which is of localized excitons hopping from side to side, you absolutely cannot explain this result. So this is what this looks like sort of in the FRET regime, right? So with FRET, you get actually exactly the result you measure for normal regioregular disordered P3HT films, which is a very, very low diffusion constant, okay? But if we include long-range coupling in these films, and we can get something else. So what I mean by that is now we have not just the kind of localized exciton picture in this system, but we also appreciate that there are higher lying states over here, right? So what that means is that when we talked about, when we initially excite our exciton, we form a kind of a wave-like state, right? Which is high in energy. And then that undergoes scattering and is localized. And normally we consider in quantum mechanics, generally speaking, the path from delocalized excitation to localized is one way, right? So once something localizes, it doesn't really go back to the delocalized state because that's normally uphill in energy and quite significantly uphill. But in these systems, it seems that we can actually go from the localized exciton, which would normally be doing only FRET, which would be very slow. We can actually go back to delocalized excitons. And this is shown here. So this is the inverse participation ratio. So it tells you essentially how large the exciton is at any point in time. So you can see that the exciton is essentially, it follows this 1, which is basically, so most of the time of its lifetime, the exciton is localized, but very occasionally there are these jumps. So you can see these over here. So very occasionally the exciton jumps and becomes delocalized across a number of molecules. So what's happening is the exciton is sitting there, localized, and then something happens and it goes up in energy, it becomes delocalized, moves very quickly, and then relocalizes. And then it sits there for a long time, and then again it becomes delocalized and moves very quickly and relocalizes. So you can think of this as kind of a jumping motion in time, but now mediated not by FRET. You're taking very, very large jumps in space, which are mediated by delocalized states instead. So the question is, what is causing this? And the answer is, this is being caused by electron-phonon coupling. So organic semiconductors, of course, are made mostly of carbon-hydrogen and carbon-carbon bonds. And there's a lot of vibrational energy in these bonds, right? So the carbon-carbon stretching modes are normally at about 1500 wave numbers. So that's about 180 MeV. And these are very fast modes, 20 femtosecond modes. So what can happen in organics, and you can see this in just a photoluminescence spectra when you look at the vibrational peaks, and you can see the 1-Rees coupling essentially reflected in that. The excitons are very strongly coupled to these vibrational modes. So these vibrational modes essentially provide the exciton energy to jump up in energy for a small amount of time before it is relocalized. So you delocalize it with a vibrational kick, it moves, and it will relocalize. Okay, so this is a new framework that we are proposing essentially for exciton transport. So the traditional one is FRET, where we just move energetically from side to side and basically downhill in energy all the time, and we can move only a small distance. Here within this transient delocalization regime, we transiently, that is for a short amount of time, we go from a localized state to a delocalized state, which can then move very rapidly via long-range coupling in the material, long-range Coulomb coupling, and then relocalize. So although this process lasts only for a few femtoseconds, when you are delocalized, you can move very, very large distances. And so this is a kind of new and interesting regime for organics. And it can only occur when we have this long range sort of coupling. So we need some long range structural order to make this happen. We don't need very, very strong side-to-side coupling. So this is not like the requirement for good charge transport, where you need very, very strong side-to-side coupling, or for coherent energy transport, where again, you require very, very strong side-to-side coupling. Here we need kind of intermediate scale long range coupling. The exact side-to-side coupling is not important, and side-to-side disorder is actually not very critical in this, which is very key because organic semiconductors are not good at very, very precise side-to-side, very, very strong coupling. There are only a few examples like very strong J aggregate set type systems where that's really possible. And then of course, dynamic disorder shatters that. Here, the dynamic disorder is actually helping us by providing the energy for the exciton to jump up to these delocalized states. So in fact, this mechanism kind of takes advantage of the thing that normally breaks transport in excitons, which is coupling with electrons, so the electron-phonon coupling. So we've demonstrated this sort of mechanism at play in a couple of papers, but actually, we think, and there's now theoretical evidence from other groups. There's this very nice paper from the Bloomberger group, which has recently come out, which suggests that this picture of transient delocalization is basically general to all organic semiconductors, which have some order or are partially ordered, right? So that is to say, many of the materials which we are working now, so molecular crystals, small molecule, even solution process films, non-fullerene acceptors like Y6, etc. All these systems have, some sort of partial order in them, much more so than, say, the polymer materials that we were working with 10 years ago. And all these materials seem to show this transient delocalization effect to a smaller or larger degree. So for instance, for Y6, for instance, the exciton diffusion lengths have been suggested to be much larger than 10 nanometers, perhaps 40 nanometers or something. And we believe that it's due to this transient delocalization mechanism. So essentially, this means that this framework of FRET, which we have talked about for inorganic semiconductors, we've used it to model our materials for the last 30 years. We now have a newer mechanism, which now better, more accurately captures the materials we're dealing with. It also gives us design rules. So the thing for us to do is to kind of ensure that there's long-range structural order in these materials, and the exact neighbor-to-neighbor, side-to-side coupling is actually not so critical. And so it should be, I think, perhaps in 5-6 years' time, we should be able to build systems just built on simple bilayer heterojunctions, which will achieve efficiencies, perhaps even beyond 20% for OPVs, because we essentially don't need to have these very complicated bulk heterojunction systems. So I think this is a key turning point for us in understanding this, and then we'll be able to engineer materials which will kind of take advantage of this behavior. Right. So with that, I'll switch to, so that's our kind of, current best picture, our best methodology for this. I'll now tell you a story about, what we could do even beyond this exciton phonon coupling transient delocalization methodology. And that is to couple excitons directly with photons, right? And so the work I'm going to be talking about is covered in this paper, which came out in Nature Com last year. So many of you will be familiar with the concept of polaritons. For those of you who are not, the idea is that when you put an exciton in a cavity, and a cavity is just something that confines light, so a set of mirrors or some more complicated nanostructured antenna, where you have essentially light bouncing back and forth between your two mirrors or two antennas, and where you can enhance the electric field, right? So if you put an exciton in this kind of system, you get a coupling between the exciton and the photon, right? So traditionally, if you don't have this kind of coupling, you have your exciton band, which is basically more or less flat, and you have your photon band in the system in momentum space. But if you can get strong coupling, then instead of your exciton and your light mode, you create a new hybridized state, the polariton, which is a mixture of your photon mode and your exciton mode, right? So this is a new quasi-particle, a polariton. And of course, polaritons are well studied in inorganic systems and equally in organic systems. But the key thing is it normally requires you to have a good cavity so that you can have a high Q factor. That is to say, you can confine light really well and couple very strongly with the exciton. So in a normal, just organic semiconductor film, we normally never talk about polaritons. We talk about excitons because we don't have a cavity. And so we set out some years ago, and we were doing experiments in a range of different systems. So we have a classical conjugated polymer here, PDA. Those of you who have read very old literature from the 1980s on organic semiconductors will be familiar with this molecule. We had a classic J aggregate system, PIC, and we had these PDIs, so these polydiamides, nanofibers, right? So we were studying these systems, and we noticed something very, very interesting in all of them, which is the following. So we did our pump probe microscopy technique in all these systems. You can follow the color scheme here. So we have PDAs in the blue, this J aggregate system, PIC in the red, and our PDIs in the green. So what you can do over here, you can see we excite our sample and we're imaging the flow of excitons in time. So you can see at t equal to 0 femtoseconds, so immediately after we excite, we have a spot which is basically exactly the size of the spot we've excited. So our focus pump spot, we get this sigma equal to about like 130, 150 nanometers. This is what we expect from the diffraction limit. But then very quickly in time, within 20, 30 femtoseconds, you can see that this spot blows up. So it goes from about 134 here, the sigma, to, it almost doubles, okay? So it's a very, very rapid expansion. And you can see the spots that we are getting here are not sort of circles, as it were. You can see the elongated shape. So these are all sort of one-dimensional polymer kind of they're all kind of nanobelts or nanofibers, which are one-dimensional. And so we're sort of getting the spreading of excitons along those fibers. But now we're getting very, very, very rapid motion in these systems. So if you plot this kind of as a function of the change in the shape, so kind of you can think about it, it's the mean square displacement. In all these materials, you see two regimes. So you see this sort of R1 regime and R2 regime. And we focus on the R1 regime today. And essentially what you get is that you get a velocity. So that exciton is moving at about 10 to the power 7 meters a second for about 50 femtoseconds, okay? So at very, very early times, for about 50 femtoseconds in these systems, the exciton moves at 10 to the power 7 meters a second, right? So at 10% the speed of light in these organic semiconductor films. So there's no cavity, there's nothing here. It's a glass substrate and the organic semiconductor film on top of it, right? Created by spin coating or drop casting. And then essentially you have this very, very rapid motion of the excitations moving at 10% the speed of light. Things then slow down and move a lot slower, but actually this R2 regime is also still very, very fast. The diffusion constants are well above 1, but we'll talk about that perhaps another day when we have more time. But the question here is, what explains this R1 regime where we're having these excitations moving at a tenth the speed of light, and they move up to 250 nanometers. So they move very rapidly, and then they stop and move slower, but still very fast. So if one looks at the absorption and reflectance spectra of these films, one finds actually something very interesting. So if you look very carefully, if you look at this is the sort of the reflectance spectra, and this is the absorption spectra, and you can see actually at the peak over here we get a splitting in these materials. So in fact, in this organic semiconductor film, even though we have no metallic cavities, no nanostructured kind of antenna system, the film itself is split. The absorption spectra is split into an upper and a lower polariton branch. So instead of a nice, just simple absorption spectra you would expect from the molecular system, which you do get in the solution, in the film, you get this splitting into upper and lower polariton branch. And this splitting, so the film is not a very good, it's not very strong coupling. The coupling is only about 20 to 40 micro EV. In a very, very good cavity, you would expect hundreds of MeV of splitting. Here we're getting only something about a 10% of that. But we are actually forming, just in these native organic semiconductor films, we are forming exciton polaritons. And the exciton polariton is actually the basic excitation in this system without any metallic cavity, without anything going on, right? So we can achieve just in an organic semiconductor, we can just create exciton polaritons as the basic excitation, right? So this is kind of amazing to some extent, but actually it turns out the explanation is quite simple. And if you model, if you do some optical modeling, and if you kind of work out how this works, essentially what's happening is you have your film and it has a refractive index contrast with whatever is outside it. So for instance, air on the other side. And that refractive index contrast is enough to confine light a little bit. And what you find is that you confine, say about 4% of the photon mode volume is confined, right? So if you had a really good mirror, you would be able to confine all the light in it. This is not a mirror. This is just this is a very poor mirror. You can think of it as a very, very poor mirror, but it's only confining about 4% of the photon mode volume. But even that 4% is enough to give us, this kind of splitting that we are seeing here, which is a few tens of MeV, and it's allowing us to generate this exciton polariton state and allowing us to move those excitons coupled with the light mode now, and it's dragging that along at a 10th the speed of light, right? So you're mixing a little bit of photon character into your exciton, not very much, just a little bit, but that allows you to move the exciton at 10% the speed of light over hundreds of nanometers within 50 femtoseconds, right? So it's kind of it's an incredibly fast motion of the excitation. And we did further measurements to and show this. Essentially, this is a measurement of photoluminescence, time average photoluminescence versus intensity of excitation. So if you take the single molecules or solutions or disordered films and you measure photoluminescence, you see classically a curve like this, right? I increase my laser power and my photoluminescence increases. And at some point, I kind of saturate the material. I have a lot of annihilation in the material now, and my curve saturates. So this is what you'd expect from kind of any kind of laser dye, any organic semiconductor will behave like this. Now I take these films I formed, which are now, I'm arguing that they act as exciton polaritons, and we actually see this behavior. So you see, as we increase the laser fluence, we actually get an increase in PL, and then a decrease, and then oscillatory behavior, right? So what these are Rabi oscillations of my system, and this is at room temperature. And what is happening is that my entire area that I'm exciting, which will have something like 1 billion molecules in it, 10 to the power 9 molecules, that entire system is emitting from this polariton state and emitting as one quantum emitter, right? So the entire system emits as one. So instead of having individual PL from all these molecules, we get emission from this one coherent system. And so this is acting as a single quantum state at room temperature, and we get essentially Rabi oscillation. This is what you would expect, from instance, from an atomic system. So if you pumped cold atoms, this is the kind of thing you get. Or if you take semiconductor quantum dots or 3-5 quantum dots and pump them at low temperature, this is the kind of behavior you get, right? So that we can get from an organic system, which is solution processed thin film at room temperature, right? So this is kind of an extraordinary sort of behavior which you would never think that a disordered organic semiconductor could show. So it's a sort of quantum emitter at room temperature. So just to summarize this work, essentially what we've shown over here is that under the right conditions, organic thin films can actually have polaritons directly without having any confined in any mirrors or having any nanostructured antennas, anything like this. Just the bare organic semiconductor, the refractive index contrast with the air or glass on either side of it can allow you to confine a little bit of light in that organic film. And that is enough to essentially imbue into your exciton a little bit of light-like character. So your excitons are not quite excitons, they're polaritons now, very weak polaritons, but they have enough photon character that you can move them at 10% the speed of light over more than 200 nanometers, right? And this is a universal phenomena. It has kind of no chemical requirement. The only requirement is that your film, the organic film you formed, should have a high absorption, right? And there should be so it's not reactive, there should be a refractive index here, contrast with the surrounding environment. So as yet, we don't believe, the question with this mechanism, which in some ways is the ultimate limit for, I think, how fast we can move organic excitons, because of course the coupling to light is the ultimate thing. That's the fastest way we could do it. Over here, I think the challenge now is to find clever ways to engineer devices to take advantage of this phenomena. As I said, the material requirements are very universal. All we need is a high absorption coefficient from the material, which many organic materials already have, even most in some ways. And we need to engineer a kind of proper refractive index contrast. And then we can have, I think, a range of devices, lasers, photovoltaics, etc., that could be taking advantage of this phenomenon. So this work was done primarily by my student Raj, and in collaboration with Professor Andrew Mazur, who is now at the University of Cornell. And you can read more about it in this paper. So I'm nearly at the end of my talk. Sorry, I've taken a little bit longer than expected. So just to say that, these kind of methodologies we're using, we're also using in a range of other systems. So for those who are interested beyond organic semiconductors, We've looked at recently quantum dots. So these are colloidal quantum dots systems, including perovskites and quantum dots, perovskite quantum dots, etc., things like that. And you can read about more of those in these papers. We've looked at three-dimensional perovskite systems, which are very popular nowadays. And we showed that you get ballistic electron transport in these systems at very early times. So that's a Nature Physics paper from a couple of years ago. We've looked at more exotic quantum systems, such as this material Tenise, which has room temperature exciton condensates. And we can see collective mode propagation. And something that we have done more recently is to kind of extend these methodologies to actually track ion transport in electrochemical materials, especially battery electrodes. And we have shown that we can directly image in real time operando within working batteries, the flow of ions and the phase transformations that happen during lithiation, delithiation of these materials. And you can have a look at this paper we published in Nature about a year ago now or so. With that, let me just thank all the people who have done the work. So of course, my group who actually do all the work. I only give the talks. They do all the actual work in this. And our fantastic collaborators from around the world who help with the theory. So Xiao from San Diego, who helped with the polaritons, David from Mons, who helped with the transient delocalization, and all our collaborators on materials from Paris for some of the polariton materials, Ian Manners for the transient delocalization-based materials, and Andrew Mazur from Cornell, who did a lot of, who kind of helped us a lot on the polariton stuff. And with that, let me just end with a summary. So hopefully I've shown you, what our previous understanding of kind of FRET-based transport was in organics, and these two new areas. So the transient exciton delocalization is something that's happening in our materials now. In the materials you are working with, the devices you're working, this process is already going on. And if we can learn to engineer the materials better, it'll allow us to make much more efficient devices, I believe. And this exciton polariton mechanism I talked about, this is something, perhaps for future years. And here we need to think about kind of new device designs really to take advantage of this photon exciton coupling to really build a new generation of, optical and electronic devices. And with that, thank you very much. I'll be happy to take any questions.
Okay, thanks for your very great and deep and professional talk about the Exatron transport in the organic semiconductors and other systems. Now it's time for questions or comments. Firstly, maybe I think in the meeting room there is a question from a student. Maybe I repeat the questions.
Sure.
Thanks for your professional. Thanks, Professor, for the wonderful report. I have a question. I would like to ask: is there any good strategy that can effectively inhibit the ionization and the diffusion of exciton to realize photostable organic electronic devices, such as organic transistors? Can you understand these questions?
Yeah, I think so. So essentially, what the question is asking is more on photostability of materials. And so, there are two ways to do photostability, right? One is that you, so for instance, the classic challenge in photostability is blue OLEDs, right? So many of you will know that we have, as a field, we have struggled with blue OLEDs for basically more than 20 years. And the problem of that, which then is the same problem in some ways in OPV and OFETs, etc., is that you get high energy excitons fused together and then they cleave the carbon-carbon bonds, right? Or whatever bonds in the system. And this leads to photodegradation or, some kind of photoisomerizations, things like this. So in nature, you have the very same problem, right? So plants have to deal with the same problem. And the way they do it is to rapidly dump the energy, right? So if you have unwanted photoexcitations, you rapidly dump the energy. So you have carotenoid molecules, for instance, in plants, take singlet excitons and rapidly convert them to this 2AG state, which is much lower in energy and has double triplet character. And so you halve that energy and then it rapidly goes down to ground state. So if you're talking about photostable molecules, then diffusion, you want to kind of, there are two choices, right? You either get the the energy to diffuse out of your system, or you build in other chromophores which can rapidly dump that energy, right? That's kind of the normal way we do it. So for instance, maybe some of you know this, but for instance, in silicon solar cells, right, you have UV absorbing molecules, which absorb high energy UV photons, which would damage the silicon and then rapidly dump that energy, right? So these are standard molecules. You can actually go on Alibaba and buy 1 ton of them for about $100 US. You can check it out. It's quite incredible. So very, very cheap molecules, organic molecules, and they absorb UV light and dump that energy down in a few picoseconds so that they can dissipate that energy and provide photostability. So I think, if you're talking about photostability, then there are different aspects to it. What you want is to avoid excitons finding each other. But this can be tricky. So what you then need to do is make sure that your coupling is such that excitons can't move, but charges can move in an OFET. But I would suggest that in an OFET, since you don't want to interact with light, it's easier to just have some other layer there which absorbs the high energy photons, and a lot of these materials are already available. In an OPV, of course, it's more challenging because you need to absorb all the light. And over there, our best option is to move the excitons as quickly as possible and dissociate them, right? Before those excitons can annihilate with each other and have a chance to break bonds in the system. So in fact, if you have a very high efficiency organic photovoltaic device, it should be very stable, right? Because you're using all that photon energy very efficiently. You're not wasting it. You're not kind of using it to break bonds or create heat in the system. You're using it to generate charges. So the efficiency in OPV should correlate quite well with the photostability in the end, if we have good materials. I hope that was helpful.
Okay, thanks for your detailed answers and explanation. So any other questions or comments?
Hi, Professor Rao. Thank you very much for your very comprehensive talk. My name is Gao Xiong, under the supervision of Professor Wenping Hu and Professor Xiaogang Liu. And I have 2 questions about your talk today. The first question is about the first topic of your transient dislocalization of the exciton. You showed that the energy fluctuates during the exciton delocalization. I want to ask if the excitation energy is related to this mechanism. I mean, if you use a UV light or near infrared light, will this influence exciton transport rate?
Yeah, so this is a good question, and the answer is basically no, because this mechanism is happening in equilibrium. So you excite your sample with whatever photon energy you want. You can, let's say, double the band gap. You excite very high up in energy. That will rapidly cool down within a picosecond. It will cool down to the band edge, and then you can see that in this mechanism, this goes on for nanoseconds, basically, right? So these are all cooled excitons, which can then hop back up. It's an equilibrium process, more or less, or a quasi-equilibrium process. So your initial photon energy is not relevant. You can you can excite this wherever you want, and you will still see the same mechanism, because those initial excitons, the hot exciton states, they've already all cooled down in the first few hundred femtoseconds, the first picosecond, to the band edge. And then those are the localized states which are then doing, hopping up and in time. So this is a general process. Something I didn't point out, which I should have mentioned, this transient delocalization. I've talked about it for excitons, but in the last few years, the charge transport community, so the OFET community, has also done a lot of work on a similar mechanism, which they call transient localization. Actually, it's the same thing. They just pick a different word for it, where charges do the same thing. So in their picture, the charges are localized, and the charge, again, because of vibration coupling, becomes delocalized, moves and localizes. And so essentially, again, that's a sort of quasi-equilibrium process. How you made the charge, how you made the exciton originally is no longer relevant. So that memory is not there in the system anymore.
Okay, thank you. And the second question is about your second topic for the cavity-free polariton formation, and you showed that the polariton formation need a strong light field to and interaction with the exciton. And I know in some organic materials there are charge transfer excitons, and they have a self-trapping effect. It means exciton may localize, and I think in this circumstance, it may also have some strong interaction with the light. Will this charge transfer exciton, the self-trapping of this charge transfer exciton, will also contribute to this polariton formation?
Maybe it's a bit. So basically, the systems we're dealing with. So for instance, in the PDAs or the PICs, we don't really have charge transfer excitons, right? So PDA is just carbon-carbon bonds. So normally in a charge transfer type exciton, you have a donor part on your molecule and acceptor part, right? Which are all the kind of polymers, the near IR polymers we work with in organic PVs, etc. You have a slight donor acceptor configuration. So I think it's a little bit hard to say. So one of the problems if you have charge transfer states is that because your donor and acceptor are spatially separated, normally your absorption coefficient is lower, right? Because the transition dipole moment is lowered because spatially the electron hole overlap is not as good as some in a normal organic system, right? Where you have direct pi star transitions with strong electron hole wave function overlap. So normally if you have kind of shifted that, that's, it's kind of like the equivalent of an indirect band gap in organic semiconductor, in inorganic semiconductor, right? Where you need to bridge K space. So normally all organic charge transfer systems, especially like TADFs and all, they have much lower absorption strength. So from the point of view of this effect, actually, I think it would be detrimental, because really what you want to have is the strongest possible absorption in your molecule, right? And in the film you form from those molecules. So these systems that we dealt with are kind of not charge transfer. They're kind of very much pi star transitions, basically, with very strong orbit electron hole overlap. So it's a good question. We haven't looked at charge transfer states. It might still be enough absorption character that can work. But essentially the main thing is to have, strong absorption such that you can confine a little bit of that light mode, right? So if you think about, what a good cavity looks like, some of these kind of cavities will have a Q factor of like 5,000, 10,000, 100,000, etc. Like in when people do quantum electrodynamics experiments in very high Q cavities, they're dealing with Q factors of 100,000. We are dealing with a Q factor of like below 10, So it's a very, very bad cavity. It's hardly a cavity at all, but it's enough of a cavity that you can actually move the exciton so fast, right? So that's the very surprising thing, because you would expect that, there would be no effect like this at all. But actually you look carefully and you can see it, very clearly, even in just the simple, reflection and absorption spectra, you can clearly see these splittings. So that's, I think for me, it was very surprising. And of course, then you look at the simulation and okay, yeah, right, that makes sense. Amazing. But actually, a priori, I would never have thought this was possible. But that's what it turns out to be. But that's the fun in science, that always there are things that are unexpected.
Thank you very much for your answer. And I also have a personal inquiry. I really admire your research work. Could I apply to join your group as a visiting student, PhD students?
Yes, send me an email later and we can discuss.
Okay, thank you very much.
Okay, thanks for your questions and the answers. And I think Xiongao can contact Dr. Rao for the future study. Yeah. And any further questions or comments?
I have some questions.
Oh, Shashiding, yeah, please.
Thank you very much for your talk, Professor. Since you are an expert in the transport mechanism, instead of many classified transport mechanisms such as hopping or band-like, according to your introduction, can we simply use the delocalization length and the energetic disorder to describe all of the organic systems, no matter in organic small molecules or polymers, thin films or single crystals?
Yeah, absolutely. I fully agree with you. That would actually be a much better and much more comprehensive way to do it. So I think you're exactly right. So if we can think about, what the length scale is and what the amount of disorder is, then we can move beyond this delocalize, this sort of more simplistic, and we can kind of put all these systems on a kind of common framework and then look at them. And in fact, if you have a look at this paper here, which I've cited, which is from the group of Professor Bloomberg. So they do it's a theoretical paper where they, in fact, they do something like what you're describing. So they compare a number of different systems, such as tetrazine and naphthalene and some NFA systems, etc. And they essentially look at this delocalization parameter in all these systems and compare with the kind of energetic disorder to some extent. So this is a kind of first attempt, I think, from a theoretical point of view to do exactly what you said. And I think, in the next few years, as we can do more experiments like this, as the computational methods become better as well, we'll hopefully be able to take any system that we make or that someone comes up with and kind of, work out, if we know the crystal structure, then we'll be able to put it within this framework and maybe predict directly how well the excitons will transport in that system. I think, this sort of predictive computational power will come about, hopefully with the help of these kind of experiments, that very soon we'll be able to directly, engineer a molecule, predict, how well it would work within this framework without having to just think in the FRET picture. But I think, yeah, in a few years, we should hopefully be able to do that computationally, just basically predict based on the kind of delocalization length and disorder, how well the excitons will move. That's our aim.
Thank you very much.
Yeah.
I'm really looking forward into that mechanism can unify all of the present transport mechanism, since they are so complicated, because actually in most of the thesis, I always found that they will classify the materials into thin films, into single crystals, or into small molecules or polymers, but it's too complicated to study them. And my second question is about when you study the Exatron transport, do you find any big differences between the polymers and the small molecules?
Dr. Rao, can you hear us? Hello? Hello?
Hello.
Oh.
Hello.
It seems there are a problem about the internet. Now it works. It works again.
Yeah. Let me.
Maybe Shashading should repeat her questions.
So again, I have to repeat my question.
Yeah, sorry. If you could repeat your second question, I don't know what happened. It just the connection went off or something. Okay. Yeah, please go ahead.
Oh, okay, thank you. My second question is about when you study the Extern transport is.
I think her connection.
Another question about Shasha.
Is there any big differences between the?
We can hear you again. Go ahead.
I guess, Shasha, maybe you can turn off your camera. Then you repeat your question again. Yeah.
Yeah. Is that better?
Yeah, go ahead.
Yeah. My second question is that when you study about the Exciton transport, is there any big differences between the organic small molecules and polymers, such as P3HT?
So it depends on essentially how this process, right? So I showed you over here, for instance, if you have normal P3HT films, the Exatron transport is very poor because the films are very disordered. If you can make ordered films in this polymers, then you can have very nice transport lines. So essentially, it's not the base molecule, but it's how they are ordering them that matters. So you can take the same P3HT polymers and kind of make very ordered films out of them and get very nice transport, or you can have a very disordered film and get very bad transport. The thing with small molecules is that normally small molecules order better than polymers, just on average. If you don't do anything else, if you just spin coat a small molecule film on average, you'll get better ordering and you'll get better exciton transport. This is why, for instance, the NFA systems, Y6, etc., which are very popular materials now, they seem to show better exciton diffusion, and because small molecules just generally pack better than bulky polymers, right, with side groups, etc. But if you can process those polymers, then you can do, you can still get very good transport through them. But this is an area we're exploring. I don't have a lot of data on it. I don't have like 100 systems to show you. But maybe next time I talk to you, we'll have 100 systems and we'll be able to put all of them in a common framework. And I think, we'll be able to do that very soon.
Okay. Thank you very much for your explanation. That's all my questions. Thank you. Sorry for the internet.
No problem.
Okay. Thanks, Shesh. Thank Rao for the answers. And any further questions or comments? Maybe, Doctor, I have two small questions. The first one is about your first part. At the end of your first part, you mentioned the long-range ordering is the key for the long-range transport. Does it mean the high mobility, high carrier mobility in organic semiconductors is beneficial for the transport, exciton transport?
So not necessarily, because essentially, in fact, the requirement for high mobility of charges is normally that you have that you require kind of nearest neighbor coupling, and then you need long range crystallinity. So actually, it's harder to move charges than to move excitons, because what happens, if you can think about very simply, right? If you have a charge, it needs to go through this molecule, the next molecule, the next molecule, so on and so forth. It can't jump through space. It needs to actually transport physically. But your exciton can jump from one point, because it's a Coulomb interaction, it can jump through space from here to here. So if your energetic landscape is like this for the charge, then your charge will get trapped at each point. Whereas for the exciton, it doesn't care. It smooths over and it jumps. So in fact, the real thing is the long range order for excitons, which is not so important for charges. So in principle, there should be systems where we can have both very high charge mobility and exciton mobility. But in practice, the way we do it right now is we kind of engineer them sort of not by design, but by serendipity, by accident, we wind up with systems. But if we can understand better, then we should be able to, generate systems where both things are kind of work very well. But I think we in some of the molecular crystals, this might already be happening. So for instance, AC in molecular crystals, for instance, might be showing some of this already, but I can't fully comment. We need to do more work, but it should be possible to have both very high charge mobility and exciton mobility in the same systems.
Okay, thank you. And another question is there some relationship between the exciton binding energy and the exciton transport? Because I know if the exciton binding energy is too low, maybe it's unbeneficial for the transport, because during the transport, maybe the exciton will be or how to say?
It will be dissociated. Yeah. No, it's interesting. I mean, you can make based on theory, you could argue either way that it should be okay, or in fact, the fact that if you think about it, if you're saying if you have a low binding energy, then you can have a spatially more, like electron hole overlap can be lower, which means it can be spatially larger, which you could argue could lead to a favorable electron hole kind of like a exciton coupling under circumstances. So it's not clear, like it could be either way. I think we don't have experimental evidence, so I won't say. We hope to measure it in the next year or so and be actually able to comment on that. I think right now it's a bit unclear. It could be detrimental, or it could be, it comes back to this question that someone asked about charge transfer character and things like this. It could wind up being better, but at the moment I couldn't say. I think it'll depend on particular systems and how the order is in with the system. It might be either detrimental or good depending on the order in the system. So I can't say directly right now. We need more experimental evidence.
Okay, thank you. Thanks for the reply. Is there any further questions or comments?
Hello.
Hello.
Yes. Can you hear from me?
Okay, I can hear you. You can speak. Yeah.
Okay. Yeah. Thank you, Dr. Rao. So, for your last talk. So, I have a simple two questions. The first one is, of course, is related to the first topic. So, you said the exciton can have a transient delocalization, right? So, do you know the delocalized state? Do you know what character of the delocalized state is fully do you know about it? And the second, how about the energy difference or energy offset between the delocalized state and the localized state? If the energy gap is very big, how the vibration can promote this kind of transition, right? Okay. So of course, if the energy gap is very big or small, so finally, this kind of transient delocalization is dependent on the systems, right? Dependent on systems.
So yeah, so it's a very good question. So I think actually, if you have a look at this paper, which hopefully the recording will be available. This is a paper from the group of Stefan Blumberger, which does a theory. So they look at more systems than us, and they look at some well-known systems like A-scenes and Y6, etc. And so they actually they have calculations for all the energies that are expected. So they have nice numbers that you can kind of look at from over there for the, what is the energy of these delocalized states versus the localized states, etc. So I think that's actually better than what I can tell you because they've looked at more systems than we have because it's a purely theory paper, whereas our paper is experimental. So on the energy gap, the energy gap in these systems, if you imagine what a CC stretch can do, right? So if I have the CC stretch is 180 MeV, that means, it can move that exciton, say 100 MeV one way or the other, right? So 100 MeV is quite a lot. And so these delocalized states are not like, 500 MeV above. They're maybe, tens of MeV, 100 MeV above. And so it appears that that is already enough to do this. So if you had more energy, then perhaps you could go even higher to delocalized states. But because in organic systems, you already have such high frequency molecular vibrations, 180 MeV, CC stretches everywhere, and always present, then you always have this, this amount of energy, 100 MeV, you can always play with it. And so that is, I think that's what is kind of cool in the organic system, that you always have this access to these 100 MeV or so phonon energies. So that's kind of always present and allows you to do this. And you can actually never get rid of it. It's always there. So that I think is the answer to how you do this. So for instance, I mean, as part of this paper, I don't have a graph here, but we've looked at the ultrafast Raman, and we can see very clearly the singlet exciton is coupled to these high frequency 1450 wave number modes, which are oscillating the energy in time. And that's always happens basically.
Okay. Yes. So yeah. So do you know what kind of vibration lead to this phenomena? Is high frequency carbon-carbon exchange or low frequency intermolecular vibration?
So we think it is that the main thing over here is the high frequency modes.
Okay.
Yeah.
So which means might be the quantum tunneling is very important in your system, right?
The what? Sorry.
Quantum tunneling.
Yeah. So it's these are so also something that is not widely appreciated is that the high frequency modes in organic systems are 0-point quantum motions, right? So they're not thermally populated phonon modes because the energy is too high to populate thermally at room temperature. Because room temperature is 25 MeV, these modes are 180 MeV, so they're not thermally populated. So these are all 0-point quantum oscillations. So it's a purely quantum mechanical phenomena. It's not you can't explain it in classical systems because you wouldn't even have these molecular motions in a classical, if it was a classical system. So these are 0-point quantum motions around those vibration modes, and this is what's coupling the exciton. So it's a completely quantum effect, definitely.
Yeah. Hey, sorry, I have one more question. Sorry. So here is the delocalized state is no energy or high energy compared to the localized.
So these are high energy states.
Yeah. To me, according to the classic bad theory, right? So if one due to the intermolecular coupling, right? So in the fully delocalized picture, the delocalized wave, the delocalized
should be lower
state would be no energy, right? So why in your case, the delocalized energy, the energy is very high?
Yeah, so this is again a beautiful aspect of the organics actually, which is something very peculiar to molecular systems, right? Is what happens is that the reason is that the organic molecules are changing conformation, right? So if the system was static, if you had no structural movement in the system, if you had no vibration modes, then the fully delocalized state would be the lowest energy state, right? That's what you'd expect. It's the particle in the box, right? So if I make my box any smaller, that should increase the energy. It's what you see in inorganics, semiconductor quantum dots, exactly that. But over here, because the molecule can change its shape, the delocalized states can be lower because the molecule is essentially changing shape to lower the energy of that state further. So actually those states can be lower in energy because the system is dynamically changing its state. So the vibrations are actually very key here. And so this kind of trick, as it were, can only be possible in organic systems, which have these high frequency vibration modes, conformations, torsions, etc., which can lower the energy such that the localized state is actually lower in energy than the delocalized state, which from a fundamental kind of normal quantum mechanics picture, you would think is the opposite way around. But that's because the molecules are changing shape. So they actually change the state of the system. So it's a completely different quantum state than the kind of fully delocalized, structurally rigid polymer that you, or whatever system. So that's the kind of way to think about it over here, is that it's actually changed, the system itself has changed. So now that what should have been the lowest energy delocalized state is actually higher in energy. And that's again a trick you can only play with organics. You can't do this in gallium arsenide or any of these systems. So that's a beautiful thing about organic materials, is that you can do lots of quantum mechanics which are not accessible in inorganic systems. So these systems have still a lot of tricks to teach us.
Okay, I understand. Okay, thank you for your nice answer.
Yeah. Sorry, I'm going to have to leave, but I have another meeting. Some people are waiting.
Okay. Now it's time. It's already over the schedule. Yeah.
Thank you so much. I hope you enjoyed the lecture. Thank you for inviting me.
Okay. And, thanks for the very nice talk and the detailed answers. We hope to host you in Tianjin in the future. Yeah.
Yeah, absolutely. Hope to visit you in person next time. Take care.
Take care.
Good luck with all your work. Thank you.
And
bye-bye.
Bye. Thanks again. Bye.